we are going to continue with 3.5. Last time we very quickly introduced log differentiation. Let's just go over the steps for that. And then we want to apply it. Given y equals a function of x. To find y prime, you can do the following process. One, you can log both sides. And of course, the goal of this would be to simplify. Two, you would differentiate implicitly.
No.
With respect to x. Three, pretty much solve for y prime. So using this last time we derived these two equations, which was in the bonus for the quiz. So what were those? Derivative of a to the x was what? Yeah?
A to the x ln of a.
Was a to the x ln of a, so that would have been the answer to that one. And this? Yeah?
U prime, a to the u times ln a.
Right, so that falls by the chain rule to derive the outside multiplied by derive the inside. So those are the two answers here. And here the important thing for you to remember is that your a is a constant, the power is a variable. So this is a rule that you can apply when the base is a constant and the power is a variable. Or the base is a constant and the power is a function. You can apply this rule, right? So this is not exactly, it's not the power rule, right? The power rule applies when the base was a variable and the power is a constant. They are switched on you. So this would be something like, if I ask you to find the derivative of 2 to the x, then the answer would be 2 to the x ln 2. Whereas this one, an example of something that applies here, is something similar to the derivative of, say, 2 to the x squared. So now it's not just an x. And so that would be equal to the derivative of x squared, which is 2x, times the original function, times ln of the base. Okay, so those are just some examples. Okay, so we derived those last time using log differentiation. But you don't always use log differentiation, so let's talk about when we want to use log differentiation. When is this technique useful to us? One reason is for the reason why we did it here. We had a power that we didn't know how to deal with. The power rule helps us deal with when the power is a constant, the base is a variable. Here we had the power was a variable, so what we did was we logged both sides in order to bring that power down. And this is going to be a common reason why you want to use log differentiation. To avoid dealing with powers, right? Because logs get rid of powers, right? So when to use log differentiation. One, to deal with variables in a power because if the power only has constants, the power rule or some version of the chain rule will apply. Right, so basically to deal with complicated powers. If we don't have a general formula, there are cases where we do have general formulas to deal with that. But barring these nice cases here, in general, if we have a complicated power, we want to use log differentiation to solve that derivative. I'll do a simple example for you, which was also, I believe, a bonus on the quiz. I asked you to differentiate x to the x. Does anyone think they got the answer?
Not really.
Who thinks they got the answer? No, not one? Okay, so the problem is you couldn't use the power rule here because the power is not a constant. You also couldn't use that rule for a to the x because the base is not a constant. So we kind of end up in this sort of weird situation, but still, the power is really what's making it complicated, because if that power was a constant, I wouldn't have a problem. That would just be the power rule. So the idea is, I know the power is making things complicated for me, so if I want to deal with a variable power, log differentiation would be a good choice. So what I would do here is set y equals x to the x, and then I would log both sides. Now what that allows me to do is to simplify it so that I can take this power and move it down. And now what I would do is differentiate both sides implicitly with respect to x. What's the derivative of ln y?
1 over y of y prime.
Right, so it's y prime over y. What's the derivative of x ln x?
X over x.
Yeah, that's 1, but
Y prime equals y.
huh? What?
Wait, what are you asking?
I'm asking you to differentiate x ln x.
Yeah. Is
Plus
it just,
ln
is it
x.
plus ln x?
Yeah.
Plus ln x. Right? Product rule is still a thing. You can't forget any of the old rules. They will always apply. I have two functions here. One function multiplied by another function. I need the product rule. So there's one case where I leave the x alone, differentiate the ln. Then the next case, I leave the ln alone, differentiate the x. The derivative of x is 1. So this is really 1 plus ln x. And so what happens now is I can solve for my y prime. So my y prime is going to be y times 1 plus ln x. Or in other words, my y was x to the x, so the answer ends up being x to the x times 1 plus ln x. So that's your derivative. That was the answer to this question. So this is one case in which log differentiation is useful when we have complicated powers. When the power is something that's making a function complicated, you can use logs to bring powers down. And then you just differentiate implicitly. You might get a product rule here, you might not, depends on what things look like over here, but you just apply a previous rule, and it'll be easier to apply in this case. So that's one example. Here's another time you'd want to use log differentiation. Basically when the other rules are too annoying or complicated to apply. So when, usually it would be like the product or the quotient rule is kind of annoying. Not that they can't be applied, it'll just be very annoying and very cumbersome. So this is sort of illustrated by a problem that we had on the previous quiz that we did on last week Tuesday, where I think it was problem 3, where there was a problem where I said, okay, here's ln of this huge mess, simplify it. And then in problem 4 it was like, okay, differentiate ln of this huge mess, and the idea was to just use the simplified version to take derivatives of each of the individual pieces. You can actually induce such a situation. So, for example, let's say I wanted to differentiate this guy, the radical of x times x plus 1 to the over 2 power over 2x squared plus 7 raised to the 7th. And I could make it a lot worse, but let's just stop there. Now based on what we've known before log differentiation, how would you actually approach that? Use the quotient rule, but that would be very annoying to apply the quotient rule, because in to find the derivative of this, you'd have to use like the product rule with the chain rule, and then to find the derivative of the bottom, you'd have to use the chain rule. So you're doing the quotient rule, and inside the quotient rule, you have a product rule and chain rule. It's kind of going to be annoying, yeah.
So would you take the log of that whole thing and then use different properties to break it up?
Right, so that's what we would do. Because I realized that, yes, I could apply the quotient rule here, but I kind of wouldn't want to. And so what we can do is, we can simplify the situation by using logarithms, because logarithms can turn divisions into subtractions, they turn products into sums, they turn powers into multiples. So that makes for a very nice situation. So all I would do here is set y equals this mess. And then ln both sides. Okay, how can I break up the right side? Let's use the log to our advantage here. So I'm going to plug all of this into a log. Yep.
Can we put like 3 over 2 radical x, x plus 1 minus 7 times 2x squared is 7? This is dividing.
No.
Wait.
Why couldn't I do the 3 over 2 ln of radical x times x plus 1?
Because the 3 over 2 is with the x plus 1.
Right, the 3 over 2 is with the x plus 1. So the radical x is in the way, so we can't apply that log rule. The log rule is if I have log of something to a power, that power can come down, but it doesn't work if there's something else in front of it. So there's something we have to do first.
Do you,
Huh?
do you just do minus ln 2x plus 7 to 7? Can we do that or not?
Right, ln of a division is just a subtraction of the ln. So I take ln of the top minus ln of the bottom. So I'm already out of the woods with the quotient rule. I don't need a quotient rule anymore. There's no divisions left. But we can go further. What else could I do here?
Do ln x to the half power plus
ln x to the half plus
ln x plus 1 to the 3 minus ln 2x to 7.
okay. Can we do anything else?
We could bring that power.
Now I can apply the rule where I can bring the powers down. So this, the half can come down. This, the 3 over 2 can come down. This, the 7 can come down. So ultimately, what do I have now? So as the dust settles, we have y, well I didn't actually differentiate yet. I have ln of y is equal to this thing. 1/2 ln x plus 3 over 2 ln of x plus 1 minus 7 ln of 2x squared plus 7. Okay, now what? The goal is to find y prime. This is pretty much as simple as I can get it. Right, because there's no ln to break up a sum. So now we can just differentiate both sides with respect to x. Derivative of ln y.
Y
Y
prime
combo
equals
1.
Derivative of this.
1 over 2x.
1 over 2x. Derivative of this.
3 over 2x plus 2.
Derivative of this.
So
7 times.
4.
So once you go through the trouble of simplifying, the actual calculus part is pretty easy. The hardest part of this problem is the algebra. And so now what I can do is I can solve for y prime. So y prime is going to be y times all of this. 1 over 2x plus 3 over 2 times x plus 1 minus 28x over 2x squared plus 7. Or in other words, my y prime is equal to the original function times all of this. And that's my derivative. And those who are interested can do that same problem with the quotient rule, and you can report back to me which one was more doable. But ultimately, after practicing a lot of these problems, you should be able to get to this step relatively quickly. With enough practice, you can probably even do it in one shot. But if not, it takes you a couple of tries. It shouldn't be too hard to get to this point. Once you get to this point, the derivative is just kind of straightforward, and then you just multiply by the original function, and that's your answer. And that's a lot nicer than the quotient. So those are the two sort of main times you want to use log differentiation, to kind of deal with problematic powers and to kind of break things down where doing the quotient rule and the product rule kind of be really annoying in order to do that. One last thing I want to talk about is this in this section is an alternative. And it's a personal preference, you can do this or not. Maybe what you can do is try a few homework problems and doing both ways, and then whichever one you kind of feel right, whichever one feels right, you just do that all the time. So this is an alternative to log differentiation. It's using an old identity, an old friend of ours, that says if we have e to the ln of something, that's equal to. The thing, right? X. E to the ln of x is just x. Once you can plug something into a log, e to ln of that thing is just the thing, because e's and ln's sort of cancel each other. What this allows you to do is if you don't have something with an ln in it, you can write it in a way that gets an ln in it. Right? So for example, let's redo one of these problems using this identity. Let's look at the x again. So we wanted to differentiate this guy. Now it's kind of not your thing to write y equals this and then ln both sides and then do implicit differentiation. You can kind of use this guy to your advantage. What you would do is you would rewrite this first as, realizing that the power is kind of troublesome, you'd rewrite it in terms of exponentials. So x to the x is the same as I can write that says e to the ln of x to the x, because anything is e to the ln of the thing. And so now what happens is, in the power, I can apply the log rule of bringing that power down. How would I differentiate something like this? Yeah?
Can you e to the u times u1?
Right. At this point, you know how to differentiate an exponential. It's kind of why I wanted to use an exponential. We know that the derivative of e to anything is the derivative of the power times the original function. And so that's what I'm going to do. So this would be equal to the derivative of the power times the original function. The derivative of the power, I would do the product rule. So differentiate the x, leave the ln, plus leave the x, differentiate the ln, and you get 1. And this guy was just you rewriting the original function, so that just becomes x to the x again. And so that's your answer. So that's an alternative to log differentiation. It's more, you're still using logs to help you out, but you sort of don't have to do the logging both sides thing in to do it. So it might be a personal preference for some of you, that'll be fine. You get to the same answer, it's mathematically valid, so we'll stop there. Any other questions? Or any questions? I should say. Okay, that does it for 3.5. So the homework for that is due on Friday, as well as 3.4. I might have said 3.4 is due today, I don't remember, but spring break is coming up. It's that time of year when you don't really care what's going to I'll catch up in over spring break. Yeah. Okay. So we're going to go back a little bit. We're going to go back to 3.2. And this is a pretty important section in terms of applications. Here we're going to talk about linear approximation. And marginal analysis. Now, marginal analysis is usually used in a business/economics context, but there are other contexts in which it's useful. But linear approximation is useful all over the place. It's basically using a tangent line to approximate a function, which we said was the whole point of a tangent line. So I'm just going to show you how we can do that. Let's start with linear approximation. Not going to go too much into the theory here, but just so you can sort of understand what the point of this is. This is using a tangent line to approximate a function. We do this when the function is too complicated to work with directly. So we sort of encountered a situation like that when we're doing implicit differentiation. There was that question where we couldn't solve for the y even if we wanted to, so I can't really even talk about the function. But we could find a tangent line to any point of the function, and we can use the tangent line to describe the function. But this is more of, the function is semi-nice, and I want to talk about it. So here's the idea. Say I have a function doing this thing. That's my f of x. And here's a point on this function. So we're doing our approximation under the assumption that there is some point already on our function, call it x equals a, that we kind of know all the information about. We know the value of the function at that point, we know the rate of change at that point, and all that good stuff. Then there's some other function. There's some other x value, relatively close to a, let's call it x, that's for a variable, a is the constant. that gives us another point in this function. And we kind of want to approximate the output at that point. We don't really know it yet in theory, a priori, right? So now there's a notational thing that is in your textbook that you might want to understand. If you take the difference in the actual y values, the notation used to describe this distance, the actual distance between 2 points on the function, the different outputs at these 2 points, that's called delta y. So it's the uppercase Greek letter delta, and it's called delta y. It means the change in y. So now sometimes finding that value is actually troublesome. So what we do instead is at the point where we know everything that's happening, we draw a tangent line to that point. And now that same x value, we can plug into the tangent line. And the difference between the tangent line value and the original y value, that distance here, if I sort of look at that distance, the notation for that one is described by the derivative, sort of like your dy dx notation. It's called dy. That's the difference between the tangent line and the y value. So the idea here is if x is close to a, your dy is pretty close to your delta y. So measuring this y distance is very similar to measuring the original y distance. Right? You can notice that as you zoom in closer and closer, the tangent line and the function are pretty much doing the same thing. So these two distances will actually get closer and closer together. As long as your function is differentiable, you can put a tangent line there. So that's the idea. Let's actually put a formula to this idea. Let's go by the definition of the derivative. We know that if I wanted to find the derivative evaluated at a, what that is was the slope as the distance between the 2 points went to 0. So that was basically y2 minus y1 over x2 minus x1. And we take the limit as the denominator goes to 0. That was one of the definitions of a derivative. It's not the h approaches 0 definition, but it's equivalent. It uses the other version of the difference quotient. And so the idea is if x is close to a, right, which the limit talks about these two things getting close, it means that this expression approaches that expression. What that would mean is that f prime of a is approximately equal to this guy. Right, so as long as we're getting close, we can kind of ignore the limit and realize that the outputs here is going to be close to the outputs of the tangent line. Which leads us to the linear approximation formula. So this was the answer to the last bonus quiz problem. To write down the linear approximation formula. The goal is here, I can solve for f of x. So I can multiply both sides by x minus a and then add f of a. And so we end up with f of x is approximately equal to f of a plus f prime of a times x minus a. And that's our formula. This is called the linear approximation formula for f of x at x equals a. idea is this approximates f of x if x is close to a and f of a and f prime of a is known or can be known without too much trouble. Alright, so that was basically the picture was. Right. So I'm using, this is the actual difference in the y values, but I'm using the tangent line difference to approximate that difference. So I can figure out the y value at a future point. So it's if I know all the information at a, I can figure out all the information at x, or I can approximate all that information by using the tangent. Now there are all sorts of applications to this. It's usually used for predictions, of course. So there are times when you sort of only know what's happening up to this point, and none of this information is known to you. It's like in the future. You don't really know what's going to happen, but you can guess what's going to happen based on the past patterns. So doing a lot of statistics will get you up to here, but then you want to approximate what's going to happen a little time from now. And so what you can do is this linear approximation form. Right? So you can kind of guess what the y value is going to be here by just plotting a tangent line at the point that you currently have all the information about. And you might wonder if that sort of thing works. Well, it's kind of why the big banks can consistently make money. Right? They can plot this complicated function like a stock chart. They don't know what's going to happen in the future. No one does. But they're like, well, based on the statistical data, we can kind of predict this is what is going to happen a few seconds from now. And so they program all these computers to do a bunch of calculus on the statistical data, which tells you, oh, we expect the stock price to be here. And so that's going to tell us whether we want to buy and sell a few seconds from now. And these computers, they make millions of trades in a few seconds. But it's all about, they're just predicting what's going to be happening just a little bit of time in the future. And they can do this so much faster than human beings. And so it obviously works, right? It's not even something that's a question anymore. This works. Yeah, you had a question?
I was going to ask if that's actually like is that information useful to like a person buying and selling stocks, or is that only useful like you said, like a computer that just trades so quickly?
Well,
like how accurate could it be in like a day or 2 days?
Are you planning on
you won't be accurate.
the stock market?
The computers will be accurate more on like, because they're really only making an incremental change, right? Which as a person, you're not really going to do that. So really, if a computer is doing this and is doing like millions of times every second, it's really only gaining like 0.001 cents per second. But you do that millions and millions of times, then that's different, right? On the aggregate, the computer is going to beat the human. The human has to kind of look on the long term and sort of do this analysis on the long term. So if you're a person, you'd be drawing like tangent lines, right? You'd be watching a stock chart over like a year and you're trying to find patterns in that. There are ways you can do that. There are many theories on how to actually do that. But to actually apply it in practice, if you actually know a lot more information, instead of doing that yourself, you can just write a little program that can do your trading for you, and then you just don't have to watch it. You just live your life while your program is doing this thing. So if you have a strategy that you think can work, you can program the calculus into your computer and it'll do it for you. But it does work, and it can be pretty accurate. And I'm going to show you an example now, where I'm going to do something by hand that one would usually do with a calculator, and you're going to see how accurate I'm going to end up being. So here's a question. Right, you're not going to do anything complicated like stock charts in this class, but here's a very simple question of the kind of problem that you might be asked for this section. So it'll be something like, use linear approximation to estimate the square root of 3.99. So that could be like a question, right? Use linear approximation to approximate this value. Of course, in the real world, you wouldn't approximate it, you can plug this in a calculator, but the concept is what's important. I want to show you guys the concept of how one might do something like this. So the idea is we're going to introduce a function by which we can track the radical of 3.99. What function do you think would be useful? So let's say that's a function, what would I? Square root of x seems like a nice candidate, right? I want to find the square root of a number, so square root of x is a nice function to use, right? Given that I know square root of x, what is the derivative? I know I'm going to use that at some point, so I just can find it here. And so now, what do we actually want to do? You can notice that if I introduce a function in this language, what I want is f of 3.99, right? I actually want the value of this function when I plug in the input 3.99. Now, a priori, I don't actually know that, but is there a number close to 3.99 for which I do know the answer? 4. So that's a point where it has nice information. I know all the information at that point. I know both the function and its derivative at that point. I can plug in 4 here and here, and I can get nice answers, right? And it's close to 3.99. For example, 1 is another number where I would know the answer, but it's far away from 3.99. 16 is another one I would know the answer, but it's far away from 3.99. I want to pick an answer that's close to 3.99, where we know all this information. So now, note that 3.99, that's your f of 3.99. I don't know exactly what that is, but now I'm going to approximate. That's approximately equal to what? Now, how we want to think of this thing is this is the f of x that I want to approximate. I want to approximate the output of some function. And what is that approximately equal to?
Okay.
F of a
Plus f prime of a.
plus f prime of a times x minus a. Right? Now, a is the nice value for which I have all the information. X is that kind of ugly value for which, or it's a future value for which I want to predict that information. So this would be approximately equal to f of 4 plus f prime of 4 times x minus 4. So I set up a function that seems to appropriately be matching the thing that I want to calculate. I know it's the function and its derivative. I know I want this, so at that point I realize that I'm going to set my x to be 3.99 and my a to be 4. And I'm going to plug it into the linear approximation formula. Now let's see what this actually gives me. F of 4 is what? 2. Plus f prime of 4. Put in 4 here. What do I get?
1 over 4.
I get 1 over 4. This would be 3.99 minus 4. So that's 2 plus 1 over 4 times, say, minus 0.01, right? Which I can think of as 1/100th. So this minus 1 over 400, really. And that I can combine the fractions. That would be 800 minus 1. That's 799 over 400. That fraction, pretty nice number. I calculated that by hand. That's my approximation for the radical of 3.99. Now the question obviously is, how good of an approximation is that? So at this point, so that would be my answer, because that's what I could do by hand, right? I'm not going to actually And technically you could sort of start doing long division here and find what that is, but can you use your calculator to figure out what that number is? I think I wrote it down. I probably wrote it down. It's 1.9975. So that's what I would guess the answer is. What's the actual answer? Yeah?
1.99749.
8 something.
8 something.
Right? So if I were to round the answer to 4 decimal places, I would be correct. And I did it without a calculator. I did it by using a tangent line. So you can get pretty accurate. You know, I'm accurate up to 4 decimal places with rounding here. And I did it with my hand. I didn't use a calculator or anything fancy like that. Right? So this is one of the benefits of calculus. If I know something right now, and this also goes into marginal analysis. That's kind of what marginal analysis is about. I know about something right now. What's it going to be a little time from now? Calculus is one way we can actually measure that. I'll actually stop here because this is kind of where I got to in my last class. So we'll stop there. 3.4 is due next time. And I'll finish up 3.5 with marginal analysis and talk about some other things. See you guys on Friday.
So 3.5 is